And Charlotte will tell us a little bit about what kind of projects NORSAR does. So, love to hear.
So I will give you an overview of the projects that we are working with at NORSAR and the challenges and opportunities that I see for us in the next 5 to 10 years. Wait. Who did I say yes?
Just click here.
Just, yeah. No, but it was the meeting. Okay, never mind. NORSAR is a private nonprofit research foundation, and it was established 50 years ago to monitor signals from nuclear test explosions. And we use the same methods and the same data for research. And there are similar institutions like us, but like NGI, Norwegian Geotechnical Institute, but what sets us apart from the rest of the pack is that we specialize in seismology and applied geophysics. So our main job is detecting signals related to nuclear test explosions, and we are designated as the Norwegian National Data Center in operating the Norwegian stations related to the CTBT and also verifying events. And we also advise Norwegian authorities and maintain the technical aspects of this verification system. So for this, we have different types of sensors. We do seismic monitoring to monitor explosions on the ground and under the ground. And we also do infrasound monitoring. So here, these shower heads here is our infrasound array in Bardufoss to detect explosions in the atmosphere. And we also do radionuclide monitoring, and this is from our station in Svalbard, which is what you saw in the previous picture. So we have stations or arrays over Norway and in Svalbard and in Antarctica, and we use those for testbed monitoring, but also for research. So if we have a detection, then an alarm goes off at NORSAR or at my phone, and then the researcher on duty jumps up and starts analyzing the signals. So this is important in terms of verifying if there was a nuclear explosion, but it's also important to say that it wasn't. So for example, if there was a meteorite, then it's important to be able to say that, okay, this was actually not a military act. And this is an example of how we put our testbed technologies into use. So we set up a system to monitor explosions in Ukraine, and we detected how far away those explosions were from power plants to be able to report this to the authorities. And then we could also look at specific events. For example, this missile attack at the Malin train station. So here we see that on our seismic sensors. And by using seismic data, we can give be an objective data source to provide accurate timing and also accurate locations. So we get this information from the media and a lot of different sources, but seismic data can give us an objective way of looking at that. So we use our methods to create a safer society. So we do the seismic surveillance and monitoring. We also work with seismic risk and hazard. I'm not going to talk about that, but we have a lot of different ways of using this knowledge that we get. And also for investigating singular events like a helicopter crash or plane crash, for example. We also monitor earthquakes in Norway. So Norway is the country north of the Alps with the most seismic activity. It's small, but here you can see the the earthquakes the last 20 years. And we also have a website where you can get information like about historical events or about recent events. And there's also a hotline that you can call if you feel shaking. So if people think they experienced an earthquake, they will call us. You're welcome to try, but stay clear of weeks 28, 37, and 46, because that's when I'm on duty. And actually for this one, then I was called in the morning by a journalist, woken up. So that's also a way that we get information if there was an event, is that we get called by journalists or people. But we have automatic systems as well, but sometimes the journalists reach me first. We also work with microseismic surveillance, which has plenty of applications, but I'm going to show for CO2 storage and also for unstable mountain and rock slopes. So the most important thing during CCS operation is that we have the accurate event depth. So we need accurate locations, and we also need some sort of real-time monitoring systems to be able to know when to start and when to stop. So we work on optimizing the quality and efficiency of these microseismic monitoring areas for CCS integrity verification. And to do that, properly, we need to further improve our understanding of the link between injection and induced seismicity. And we also need to improve our location estimates and the event detectability. So from previous case studies, we've found that we need good azimuthal coverage, and we also need sensors at different depths to be able to resolve the depth of the event. So this monitoring can not only be driven by cost efficiency, but we need to think about what is actually effective. For CCS in Norway, we installed the HNAR array close to Bergen. And by using area processing, we can improve event detectability. But only by using these stations onshore, we get very poor resolution on the depth of the event. So we also need ocean bottom sensors. We need maybe to add fiber optic cables, both on the seafloor and also maybe in a well, to better constrain the depth. Another case of microseismic monitoring is Åknes. So here we have this beautiful landscape, we have a fjord, we have cruise ships passing by, and there's also a crack that is widening. So this place is heavily instrumented, and we have the top of the scarp, the top scarp that moves with 10 centimeters per year. And it's heavily instrumented, but only looking at the borehole data, then we see that we have these events that we cannot see on any of the surface sensors. So these episodes of intense seismicity is only recorded in the borehole, and they resemble the temporal evolution of the events resemble this precursory activity before major never mind. Major failure. There it was. So we also use our sensors. So we also use our sensors at Svalbard to monitor the cryosphere. And an example of that is using dV over V to monitor permafrost. So we do that with our Spitz array. And since we've been here for such a long time, NORSAR has a long history, then we also have a lot of data. So the potential here is to use the data for long-term monitoring of permafrost with seismic arrays. And we also look at frostquakes and for permafrost monitoring, and also we use we used ambient noise to monitor quick clay. In Oslo, we have, or quick clay is actually deposited in marine environments during glaciation periods. And as the clay is lifted up, then it's exposed to natural processes such as rainwater infiltration and groundwater percolation and erosion. And the salt that originally provided the stable structure is gradually washed out. So you're left with this house of cards that can collapse and flow and behave as a liquid. And it's actually over a large part of Norway actually has potential for this quick clay. And we also built our largest cargo terminal on it. Although I'm mostly worried about IKEA. So another reason that I'm mentioning this is because this is also one of these areas that you have the potential for cascading events or multi-hazard. So you have the quick clay area and you have a river going through. And if there was a quick clay slide, that can set off another quick clay slide and there can be flood and then there could be a fire. So these multi-hazards is also, I agree, something that actually should receive more attention. So we use Codawave interferometry to look at the changes in the subsurface in this area with quick clay. And we see changes with freezing and thawing. And we also see changes with the extreme weather humps. Another cold application. So we have a test site in the north of Norway for snow avalanche monitoring. So there we use existing telecommunication cables for real-time monitoring of snow avalanches and vehicles. I want to point out that this is used in addition to other systems, but it has been operating for the past 2 seasons, and it can tell you when you need to close the road. And it can tell you it's used to be able to know when you can close the road. So here, did it start? Yeah. So here we see an example of an avalanche and the amplitude on the dust cable. So by using dust, we can detect the different vehicles that travel along the road, and we can see how fast they're driving. So here we have an avalanche, and then we can see the car that's driving away from the impact zone. So it can also tell us if we have a car that's stuck or a car that stopped, so then probably something happened. And you can also say where that car is if you need to dig someone out. And also if you need to get there quickly. And it can also be used for road monitoring statistics. So I ran really fast through a bunch of examples because I wanted to show that there are plenty of opportunities for applications of seismology. And the challenge is to find out where our applications can actually add value. So if we take our example with the snow avalanche monitoring, then we know that we already have cameras there, but the cameras have limited visibility. So if there's snow on the camera, then you can't see anything. If it's dark, maybe if it's bad weather, then you're not seeing that much. And it's also not anonymous. So in this way, the dust can complement that. And also, we already have radar, and radar is great at detecting movements, but it cannot tell you if the snow avalanche actually hit the road. And it cannot tell you if there's still snow on the road and how much snow that would be. And this is where I think dust can add value. So I wrote monitoring systems and public perception because I wanted to emphasize that yes, there is a need for monitoring solutions, but we also need to be able to explain them. We need to be able to say how it works, and we need to make it usable for the people that need them, and so that you can get fast and easy access to information. It doesn't help if you create the perfect system if you're the only one who knows how to use it, or if no one is using it. Another point I wanted to stress is that I think one of the biggest challenges is that we need to pull in the same direction. So getting everyone to pull in the same direction. So some are working in the industry where maybe you can't share data, maybe you can't share methods, and some are working in competing institutes. And also, of course, personal ambition, and it's now more important than ever that we actually work together. So this is also an example of the dashboard that we're working on for the car detection. So it's a way to visualize, to maybe make it seem more appealing. Cute car here, cute car coming in up there. And I wanted to leave you with our 2 new installations. So we have the Troll array in Antarctica to show that we are now investing in polar research, and also the Norfox array, which is in Hamar, where we put in a DAS array close to the already existing seismic array. So to show that we're also investing in fiber. And yeah, that was it.